Okay, guys, I think we can start today's session. One second. Okay, so we are entering to the mastering sessions. Like we will be specifically discussing the ROS capabilities mainly, like the ROS navigation, ROS manipulation, and the perception side of it. Okay, that is the main thing, and then we will be seeing the deployment aspect. Like we already seen this in ROS 1, but we will be revising that in ROS 2 as well, like how to create a Docker image, how to run the container for ROS 2, and then we will be seeing how to start the NVIDIA Docker. Then also like the continuous integration setting in GitHub, okay, GitHub Actions, all this stuff, and the projects. Okay, so these is the plan for the uh, mastering series. So mainly focusing on the capability. So the first chapter was the navigation. It's actually a big topic. We had some demos of ROS2 navigation stack before. I will be maybe discussing that maybe tomorrow. I just want to set some more demo. We already have some demo, but let me see if we get more demos. But for ROS Move It 2, I already have some demo, but in the official tutorial, they also having multiple demos. And the Move It 2 is not that different from the Move It 1, so that's why I plan to discuss the same. One second. So I was trying to set up the packages. Actually, um, maybe I can start with the official tutorial so you will get an understanding. I hope you have seen it before. We will be like practicing it, and then we can see what are the things going on. One second. Okay. So this is the official tutorial. You know the official Move It website, right? Yeah. Maybe I can talk a bit about Move It, and then we can start with the examples. Okay. Okay, one second. Let me take the official website. Yes. You can also take it. Yeah. And this is the official tutorials. Okay. And I am in the background. I am actually planning to set some demos. Okay. It will act. The issue is that the demos of Move It are. I mean, they actually put it as source code, so we have to build it. I have the binaries ready, but in order to set these packages, I'm planning for these packages. So it needs some dependencies and all. So I'm setting that in the background. So you don't need to worry about it. I'm just setting it, and during the demo stage I can show to you. One second. Okay. So this is official website. I think you already know it. And the Move It 1, that is for ROS 1, and Move It 2 doesn't have much difference. Okay. So one second. Yeah. Yeah. So the ROS 1 Noitic is having the Move It 1, and in ROS 2 we have, I mean, Move It is there for Humble, and also currently it is available for Iron as well. Okay, so in order to install uh, Move It, it's pretty easy. You can do it through the apt-get, or you can build from source. Okay. In order to explore the demos, they are saying to build it from the source code. But if you have the Synaptic installed, if you install the Synaptic, you can see the Move It packages. So just search for ROS Humble Move It, and you can see the packages. So just install ROS Humble Moveit here, and you can install Moveit resources. So it will be installing some Moveit config for the demo. Okay, then you can simply go and you can check the perception. So you may have a doubt like, what is this DBG sim? So basically it is for debugging. We don't need to install it. Yeah, you can simply install other stuff, ROS control, and if you want to install CHOM motion planner, that I will be explaining. So simply install most of the packages. No need to install DBG sim. Mainly the meta package. Meta package means if you install this package, it will be installing the dependencies of Moveit. Okay, so Humble Moveit is the main package, but you can also install other packages that I have shown here. Okay, and then do apply, and it will be installing. So this is the first way. Obviously, you know how to install a ROS package from the binary, right? And second is the source code. So I will be preferring, if you want to work with the latest update of Moveit, I will prefer the source code, but it will take some time. Okay, the instructions are here, and it will take roughly, based on the computer performance, it will be taking like 30 minutes. 30 minutes, yeah, it will be taking. And again, you can build it in Windows as well, because ROS 2 you can install in Windows. Now, yeah, so the package that I am planning to build is the Moveit tutorial. Okay, so I'm just copying it. So basically, if you take the Moveit documentation, this is the Moveit documentation. It is having multiple tutorials, example, all this stuff. But the problem is that they have mentioned all this example, and they are also saying how to build the source code, all this stuff. But it is not based on the binaries. If you check it, they are showing the instruction for building in source code. Okay, so this instruction, if you just take the get start, that is the first one, install ROS 2 and Qualcomm, all this stuff. So this is a source code based stuff. But if you only want to build this tutorial, okay, yeah, you can build the Moveit from binaries, or you can install it from the binaries. And if you don't want to install from the source code, what you can do is you can simply install the binary, and you can take this Moveit 2 tutorial package from the from this. Okay, basically this Moveit 2 tutorial is not only a package, it is also having a HTML file, help file. Okay, so you can see here in the example, it include the packages. Okay, I think your first project, see, there is a CPP file. So I'm not sure it will work. One time I have tried it, but let's see whether I can do it or not. Okay, so what I did was, maybe I can show you what I did today. So I installed the binary packages, and I created a workspace, and I follow the instruction, this instruction basically. Okay, created a workspace, then cloned the Moveit 2 tutorial repository, then imported the dependencies, again that is source code, and install other ROS dependencies, mainly binary dependency, and try to build it. Okay, so the problem is that here, if after cloning, if you do this command, it's basically downloading the dependency, okay, which is mentioned in this .repo file. So if you just check here, you can see a .repos file. So imagine you are doing a project, and if you have some dependency, source dependency, which is in GitHub Okay, you can write a repository file like this. Okay, and you can mention what are the other packages required to build movie tutorial. Okay, so when you do the VCS import, it will be downloading movie task constructor, visual tools, ROS to Cortex, that is for the demo, then ROS to robotic use, serial, then movie 2. Okay, movie 2, movie resources, movie message, and pick IK. Okay, the problem is the dependency also having the movie 2, meaning the entire movie source code. Okay, so if you do this after doing this command, it will be around 52 packages you have to build. Okay, 52 packages. And also if you do the this command, there is a problem. You have to change from main branch to humble. Okay, otherwise the main branch is for rolling distribution. I hope you know about rolling. Rolling is mainly for, I mean, it's like a testing distribution. You will get the latest updates in rolling. Okay, so you can try this. Okay, and after doing the row step, you can build it using this. Okay, so that is what I am planning to do now. So one change that I did was I deleted the move it. Okay, I deleted the move it. It was taking a lot of time. So what I'm planning to do is I'm building it without the move it, because I already installed move it through binaries. It is much faster than this. So now it is about 17 packages. On the top you can see 11 out of 17 is already done. Okay, yes, so we can see whether it work or not. Yeah, there are some packages require more time. I'm not sure the SRDF DOM is already there in Synaptic. Maybe I can try that. So it's like only focusing on the movie 2 tutorials. Okay, yeah, it is. It seems like it is building. Then 4 packages left. Okay, yeah. So maybe we can discuss the concept a little. It's mostly same as the ROS 1 stuff that we already discussed. So installation, I think you already seen, right? Now regarding the concept, there is no much differences. This is architecture. I hope you remember. I will go through it anyway. So basically the concepts are the same. There is a node called move group. Okay, so which is having I mean the plugins like for planning, for trajectory generation, then obstacle avoidance. All these things are connected to the move group. And the move group, the input to the move group means, I mean, the move it and navigation stack literally is the same. Like in navigation stack, we are giving a goal position to basically to reach the destination. We are giving goal position, a robot will reach the destination. In case of robotic arm, we are giving a goal position of the end effector. So this section, right, move it commander, RVis plugin, all these things are the input to the move group, meaning it is giving the goal position. And then there is the planning pipeline, then planning scene, which is having the obstacle and the robot, which is mainly seen in the RVis. And we have the planning pipeline there. So if you give a goal position, it will be going to the planning of the trajectory, and then it will be checking the collision, and it will be generating the IK solutions. And after generating the planning, it will be going to the trajectory execution and going to the controller. So this is what basically the move it is about. Okay, and this is how the move group node works. You can see the input to the move group is like the URDF. Okay, and it's also receive the SRDF. SRDF mainly having maybe I can show you that after discussing the MOVEit config generation. Then the inputs are like the URDF, SRDF, and the configuration files. And also one of the input is a point cloud topic, okay, which is for detecting the obstacle in the robot environment and creating a 3D map of the robot environment. And the other the programming aspect from the user side, we can command the MOVEit or move group node to compute the the trajectory. From RVs we can do using Python. We can do we have the move group interface C++. So all using all this API we can interface. Okay. So in ROS 2 there are some changes in the programming side. Programming side mainly like there is two new things, that is MOVEit Py and MOVEit CPP. They have created two new stuff. Basically it's the same stuff, that is for moving the robot programmatically, but it is slightly better. Okay, I have attended this MOVEitCon basically in US last year. So before ROSCON they will be organizing MOVEitCon, and they also demonstrated the MOVEit Pro. Okay, I am in touch with the Picnic CEO. His name is Dave Coleman. So the MOVEit Pro basically is an advanced version of MOVEit, which is not only like the programming, all this stuff. It is like a behavior tree kind of stuff. Like you can program the robot like visually. You can do the visual programming. Oh, 1 second. Let me reduce the volume. So you can see here. And there was a demo of MOVEit Pro in ROSCON. So this was their demo. You can see the environment, right? I think this is happening in the space shuttle or something. I'm not sure. There is a UR5 robot, and there is a behavior tree on the right side, and you can program it. The robot will be moving. So this is the visual programming. Yeah, so we got the demo today. I mean, in MOVEitCon, we got a demo, and yeah, so I think some of the robotic companies are using it, but one problem with the MOVEit Studio is obviously the price, because it's a US-based company, and generally companies in India or other countries can't afford it because it's too expensive. So actually the CEO sent a mail to the participant that who attended the conference, and they ask about the feedback, like how they can improve the product and all. I also got some mail, and I have given some suggestions, like if they can give some academic license, that will be great, and some license for the startup. All these things will be helpful. Yeah, so so this company Picnic is doing they are mainly supporting the Moveit, and Moveit Pro is the commercial product that they have built. Okay, this is their main product. Yes, so that is about the Moveit Pro and Moveit. And yeah, so in their website you can see multiple application. 1 second. In the meantime, let me check the status of the build, because yeah, it's going on. Yeah, so we can see various examples with Moveit, both in production and hobby grade. I mean, there are a lot of applications. Yeah, so mainly the demos are using UR robot. You can see here there are simulations. This is from Amazon Picking Challenge. And in the robots, so if you are planning to work on any of this robot, it's already compatible with Moveit. I mean, you can make any robotic arm or any robot Moveit compatible. It's an easy task. I will show you that first, and then we will be moving to the programming side and demo side. Okay, so yeah, so these are the robots that is using Moveit. I mean, the list is actually not completed. I mean, there are a lot of robots using Moveit, but these are some popular one. They are, I think, I mean, if you take the industrial robots, they have a Moveit interface. This doesn't mean that they are only running on Moveit, but if you take the service robots, all these category, I think I will say mostly they are working with ROS and Moveit. Okay, so all these robots are compatible with Moveit. That's a good thing. Yeah, I think there are a lot of robots. Yeah, so I think the build is almost ready. So we can see whether the tutorials are built properly. After that, we will be starting with the Moveit config generation. Okay, the same thing that we have discussed with ROS one, how to create a Moveit config for your robot. Okay, so let me see the tutorials build properly. So I created the workspace, and after building it, I'm just adding to the bash RC. Okay. Okay, Moveit workspace. I think there are some problems. Install ROS Moveit visualization not found. I think ROS visualization, maybe I can delete it. Let me check. I can just search for it. Yeah, let me delete this and try again. Oh, wait. Yeah, it seems okay, but we don't know like whether it work or not. But let's start with the first demo. Make sure the environment is set or not. So in the getting started, they have the first quick start, which is Moveit tutorial demo.launchfy. Yeah, it seems like loading. Let's see. Yeah. I think the tutorial is working. You can see the tutorial. The robot is there. It's a Franga robotic arm. Like, I think we have done a similar demo in ROS one. So like the plan and execute. I think this is familiar to you, right? You already have seen it. Okay. Yes. Okay. So basically, I can explain what I'm doing, but I'm just checking whether the demo is working fine or not. These demos will be showing at the end of the session, and then we will be explaining with some programming example as well. Okay, so seems like the build is working fine, guys. So first we can start with the one second. Let me take the not the C++. Okay, it's actually not mentioned here. Move it configuration. Yeah, configured it. Okay, basically it's not mentioned. I can show you anyway. Oh, okay, I will show you that. It's not mentioned here. Okay, so after installing MoveIt, you can start the MoveIt setup assistant. I hope you remember that. It's actually a GUI or a wizard to create the MoveIt config for your robot. So what is a MoveIt config package? It's very simple. So if you remember, you work with navigation stack, right? Navigation stack, ROS1 navigation stack. So you created a package like Turtleboard 3 navigation. Okay, and what is the importance of that package? That package is having configuration file, launch files for starting the navigation stack for the specific robot. Okay, your robot. In case of MoveIt, it is giving a wizard. Okay, it's called setup assistant, and you can launch the setup assistant using this command. Okay, basically it's a launch file. So if you do this, you can open the setup assistant. Okay, so how setup assistant work is that if you give a URDF, you can configure the MoveIt config, and you can assign planners, you can I mean do the self collision, all this stuff you can do with a URDF. Okay, and also if you want to edit the existing MoveIt config, you can do that. So this MoveIt config is having the configuration file, launch file to start the motion planning of a robotic arm. Okay, you can compare the navigation and manipulation. Like navigation stack, you have to create a new package ourselves, but using MoveIt setup assistant, we can create a package for manipulation automatically. Okay, you don't need to create your own. Okay, so I think it's a good tool to create your own configuration package easily. Okay, so what I'm doing is I'm just taking some existing URDF. Okay, so let me search for some. One second. I'm just checking if there is any robot packages, I mean description packages available in MoveIt tutorial. If not, maybe we can download it from MoveIt itself. One second. There is a package called resources. MoveIt resources, I think it will be there. Maybe I can go to the trash and MoveIt setup assistant, planners. No, I don't. Yeah, I think I have found that, but let me see. Or I can find it from here. I mean, I just need to get a URDF. So maybe I can take it from here. Like we have just started the demo, right? We will get the URDF for that. Let me see where it is. I think it's from the resource manager. Yeah. Yeah. So let me open the Synaptic Package Manager and just search for move it resources. Okay. And you will get this package. So you can see there are a set of description packages in the resource folder. If you check it, I think we will find set of resources, Fanuc description, okay, Panda move it. So these all are the description in the resource. Maybe we can download some description maybe. Yeah, Fanuc description is already there. So we can see the installation path. It is here. Yeah, so this is a path where the URDF is placing. So I'm just need a description file. Yeah, I think this will be okay. So I'm just going to that path to get a description. Let me see. Or maybe I can directly go. I think that will be fast. So just go to the computer / opt rows humble share, then resources, move it resource, then move it resource Fanuc description. Okay, then we have the URDF here. Okay, maybe what we can do is we can directly take this package. Okay, the package is called move it resource Fanuc description. So we can try to create a new move it package using this description file. So I'm just copying this path. Oh, 1 second. Something happened. Let me take it, or maybe I can copy it. That will be easy. Fanuc, okay. Copy to documents, and now I can open the setup assistant, create a new move it config. Just going to the downloads, then just browse the URDF and press the load file. Okay, so if you do that, it will be showing the Fanuc robotic arm. Okay, make sure the package, the description package, is in a workspace. Okay, currently it is not in the workspace, but it is still loading because it's already installed. This package, this move it resource Fanuc description, it's already installed. That's why it's short. Okay, and after seeing this, you can visualize the visual and collision part of this. Okay, now going to so this is kind of wizard. Okay, so this is a start screen. We have browse, and we can give the self collision stuff. It's basically a matrix. So like if a robotic arm moves, there is a chance for self collision. Okay, like the links of robot can collide. So in order to avoid that, not only for avoiding, but in order to compute the plans properly, in order to optimize the collision detection, they are creating a collision matrix. Okay, so this is simply saying which all are the links can collide. Okay, so we don't need to check the collision in adjacent joints or something, adjacent links or something, because only chance is like for certain links can collide. So we are creating a matrix for collision checking. Okay, so if you are creating a effective matrix, then it can improve the motion planning time. Like we can quickly generate the motion planning, because the motion planning time, that is going from A to B, if the robot want to go from A to B, it involves a lot of process like collision detection, then IK, all this stuff is happening, right? So this self collision checking matrix is very important. So currently we have generated a automatic matrix, and you can increase it. Okay, you can increase it, but if you increase the sample density, then the motion planning will be taking a lot of time. Okay, so we just created it, and then the virtual joint comes, I mean, in the third option, which is like if you want to add a mobile robot, or if you want to add another joint like world. Okay, currently the first link will be base or something. If you want to add a virtual joint like world, you can add it here. Okay, so that is optional. It may be useful while working with a mobile manipulation robot. Okay, now you can go to the planning group, which is the important part. Like in order to do the motion planning, you have to add what is the arm and what is the end effector. End effector means gripper. So which all are the joints taking part in the motion planning and which is the gripper. So you can press add group and give some name to the group. Okay, group mean motion planning group. So the motion planning is doing with this set of joint. Okay, so I'm giving a group name called arm. Okay, and the kinematic solver, like the IK is also doing, right, in like along with the motion planning, the IK is also doing. So we can select the kinematic solver that we want to use. So these plugins that you can actually create, if you want to write your own kinematics IK plugin, you can write it. There is a plugin format for that. Okay, so the KDL kinematics plugin is the default one. You can do that. I mean, select that, and then you can also fine tune some parameters. So make it as default, like, yeah, and then you can add the joints. Okay, so the joint 1, joint 2, joint 3, joint 4, joint 5, joint 6. Okay, so these are the joints that is, I mean, you can take joint 6 also, because there is no end effector link. So these all are the joints taking part in the yeah, I think the base joint also, base joint is rotating, right? So we can add all these joints to the arm. Okay, and there is no end effector, by the way. I mean, maybe you can add another group called gripper, and there is no end effector basically. Yeah, maybe give I hope you understand the thing. First you have to add the arm joints. Okay, so just add all the joints, so it will be created like this. Next you have to create the group for gripper. Okay, so just give the name like gripper, and there is no kinematic solver required for the gripper. It will be like maybe fixed joints, or like maybe it will be moving. Okay, so you can add the links for the gripper. Currently I think the link tool 0 you can add it as the gripper, and link 6 is the parent. So you can see here gripper, and we have given tool 0 as the gripper link. Okay, and in the robot pose, next is like you can create a pose, like you can give it as a home pose. Okay, and you can save it like that. Okay, so you can directly call this pose and the robot will be going to that pose. Okay, it will be useful sometime. And then end effector, so you can again define our end effector planning groups, like you can give it as gripper again name, and you have to give the end effector group as gripper. I mean, that is already we have created, right? In the planning groups we created a end effector group, and the parent link of the end effector is link 6, because after link 6 we have the tool 0, so the parent link is link 6. Then save it. This is optional. And then passive join, if there is any passive join that is not having any actuation, you can give it. Currently there is no passive link. And now this is for the rows 2 control. Like these joints are controlling using the rows controllers basically. So if you want to add the controller configuration to your URDF, I think we have done similar stuff in the rows 1. We have to add the hardware interface, all this thing into our URDF, then only the controller will be working. So you can do the add interface option. So you need to simply add this line to the URDF. So it will be saying like the controller for each joint is based on position, and it will be also getting the status, position and velocity. State means the joint state. Okay, so we are commanding the robot joints using position and getting the state as position and velocity. So this is the automatic generated code. You can simply copy paste into a URDF in order to interface to the controller. And this is the controller, rows 2 controller for this is a configuration basically, YAML file. This is for communicating from Moveit to hardware or simulation. Okay, so basically Moveit is acting as an action client. Okay, and if you are playing with Gazebo, Gazebo is acting like a action server. Okay, and what happening is that the Moveit is like, it is sending the trajectory to the Gazebo or the real robot. Okay, so this trajectory is actually sending through the controllers. So you know the ROS controllers, right? So the ROS controllers, the Gazebo or the real robot running on the joint trajectory controller, the Moveit is sending the trajectory to that controller like a client. Okay, so you can use this configuration in Gazebo as well. Make sure the join names are correct. Okay, then it will be communicating with the Gazebo. Okay, then this is for the Moveit control. So this is for Gazebo actually. Okay, So there is a description here like configure ROS2 controller. By default, ROS2 control fake component are used to create simple simulation. So like if you want to execute the trajectory in hardware or simulation, you can have this configuration on your simulator. Okay, and this configuration is in the MOVEit. Okay, so by default, if you want to simulate this motion planning, you can have a fake controller, so it will be executing in the MOVEit RViz itself. Okay, it will not be executing in Gazebo or Real Robot. Okay, so I think it is currently configured as a fake controllers. Okay, and this is for the MOVEit controller, and this is for the perception. For example, if you want to add a depth camera into the robot, okay, it may be connected to some links or outside. You can connect that camera and just give the point cloud topic, okay, or depth image. So it will be converting this point cloud into Octomap, which is helpful for obstacle detection. Okay, so for example, if there is any dynamic obstacle passing nearby the robot, the depth camera can able to convert point cloud into Octomap, which can be avoided by the robot. The Octomap is basically obstacle. So when we do the planning, the robot will be avoiding that. Okay, and finally the launch file. Okay, launch file, like to start the robot, start the simulation, all this stuff, it will be automatically generating. And you can just give the author name. So maybe I can just give it some dummy. And now this is going to be the package name. Okay, so I'm just giving a package name here. 1 second. I'm just giving test MOVEit config. So basically we have to create a folder in the workspace. Okay, so our workspace is MOVEit workspace, and inside SRC I created a folder. Okay, and you have to give this folder location here. So what happening is that the generated launch file, configuration file, all files will be saved into this folder, which will in turns to be a package. Okay, I can show you that. Okay, so if you press the generate package, it will be saving and you can exit. And if you just check the MOVEit workspace and the test MOVEit config, here it is. Okay, so this is the MOVEit config packages. So if you test the package or XML, you can see the package name is also automatically created as a test MOVEit config. Okay, and if you want to work with the test MOVEit config, you can build it. Okay, you can build it using Qualcomm build package select test MOVEit config. So we can build, and then 1 second. I think it's packages select. Yeah. So it is building the package. Now we can start it. So like we have done in ROS1, there is a demo file, demo launch file, which will be launching all the stuff. Test MOVEit config demo launch. It's showing error. Let me see. I think because of the URDF, I guess. Let me see. Okay, URDF is here. So this is a configuration file that is generated, and this is a launch file got generated. We have the demo.launch file, and let's see what is happening. Actually, I'm not seeing much things. It is simply showing some issues. Let me try once more, or maybe I can build everything. Qualcomm build. Let's see how it goes. Basically, okay, so in the workspace itself, we can able to see the movie resource Fanuc description. It was already there in the source code here itself. I think it's already there. Yeah, this was I was searching for. See, so Panda description is there. Then the Panda movie config is also there. So this is the package that I am talking about, you guys, like movie resources. So let's see the package that we have created is working or not. Otherwise, we can try it with the Panda movie config or PR2 stuff. Let's see. And we have the Fanuc movie config already generated here. It's already there with the movie resources. Let's see. Okay, one package need to be built. Okay, so this is a movie config for that. It will take some time. I think the movie tutorial, I'm not sure why it is taking this much of time again and again. Okay, I think so this is how we are creating the setup assistant, guys. The movie config we are creating using the setup assistant, and after that you can do the planning like we have done for this demo. Okay, yeah, okay, and there are a lot of things we can play with the RVs plugin. So basically you can command the robotic arm using program like C++ or Python, or the easiest way to test the robot is through RVs. So there is a plugin called motion planning plugin which is coming along with Moveit. So you can simply interact with the robot using RVs. You can plan it and you can add obstacle, all this stuff you can do. So that is what it's showing the Moveit quick start, and after that they are going with the programming side. Okay, so we will try that. Okay, so let me try it again, the test package that we have built, whether it is working or not. Unfortunately, there are some problem. I am not sure. It is not showing any other stuff. So let me try to start Fanuc movie config. Let's see whether that work or not. Or let's see the name of the package. Okay, the package name is moveit resource Fanuc movie config. So just start the demo.launch, because in any movie config package there will be a demo.launch file which is starting the planning everything. Okay, and it may be executing in fake controllers. Okay, so you can change that as well. So here you can give the goal position, plan it, and then you can execute it. Okay, planning means like it is showing this is a plan that the planner got created, and yeah, so this is a planning. you can execute it. So when you press the execute now, if you have a simulator or if you have a real hardware, it will be executing that trajectory. So move it basically sending the trajectory to a simulator or hardware when we press the plan and execute, okay, or simply execute. Okay, plan is simply planning, execute is executing in the controller. So currently we are using the fake controllers, so that's why it is showing executing. Okay, yes, so this is how it is working, and I just want to show you the programming example just to get a start, and maybe next class we can continue with the programming part and also some more stuff. Okay, like we can play with the obstacle with the obstacles and all. Okay, let's see how it goes. So maybe let's see how the programming demo works. After that we can continue maybe tomorrow. I'm starting the first launch file. So this was the demo robot, and now we can try the Hello Move It package. Let me see whether that is in the tutorial or not. Okay. Okay, actually the code is there, but there is no package, by the way. Okay, so we have to create a package and put the node here. Okay, so maybe we can simply do that. Just copy paste this line. So the tutorial is your first C++ Move It project. So it is like creating a C++ package which is having dependencies, and it is you can also give the node name as well. So just go to the Move It workspace, opening a terminal, and then creating a package. Yes, we have created a Hello Move It package. This is a node code, I mean the sample code. What you need is the actual code. So we can simply search in Move It tutorial folder and you can find it. This is a complete folder, I mean code. I just copy pasted, and now what I'm going to do is I'm simply build it. Okay, so Hello Move It. Let's see whether it build or not. Yeah, it is building. After that, this is a code basically, so after that we can try to run it. We can see if there is any change. Basically, like we are trying to control the robotic arm, so it's showing again some error, guys. So maybe for now like we can just conclude. Let me see the dependency issue. Maybe tomorrow we can continue with the programming. I just want to show this demo to you, but unfortunately it is not working this time. So I will be setting up this package again, and then we will be seeing other examples. Okay, so using Move It RViz interface, you can simply give the goal position, and if you want to add some objects, you can add. These objects are actually obstacles. So imagine you put an obstacle, and so this is a planning scene basically. Okay, planning scene is what the environment around the robot. So we just added an obstacle, and if we move the robot, you can see it is showing red when it approached to the obstacle. And if I'm giving a goal position, okay, it will be always avoiding. Okay, so that is what the obstacle avoidance in Move It. Okay, so you can see it is always avoiding. And if I am just giving a goal position like this, and if we plan it, it will show failed because there is an obstacle. Okay, and I can just give another goal like this, and you can see the plan. So it is like moving like this and then going like this. It's basically trying to avoid that obstacle, but it will not handle the dynamic obstacle. In order to handle the dynamic obstacle, you can use a depth sensor and then give the point cloud. So it's very easy to configure a Move It package. You can just give a goal position just underneath. Okay. Yes, you can see instead of going to that point, it is trying to reach without colliding. Okay, so you can add scene objects like this, like you can add a mesh file. Okay, if you want to add a mesh file, you can do that. You can add a mesh file from the URL. All these things are there. Okay, so if you want to add a mesh file, I can show you that how we can do it. I'm just adding some mesh file. Okay, so I added a mesh file. This is a mesh file from PR2. Okay, and I can plan. Okay, I can do some planning. So yeah, I can do the planning like this. You can see it is going by avoiding obstacle and reaching here. Okay, so these are some things that we can do. Okay, and also you can store the scenes. Like if you want to store the scenes, you can do that. In order to do that, we need to set up a database. Okay, SQLite database. There is an instruction for that, so you can simply save this and load this. Okay, so let me know like if you have any question. I mean, we just did some basic discuss basics in today's session. Maybe tomorrow we can start with the programming and the navigation. Okay, so let me know if you have any question today. I think we already discussed the basic stuff, right? Let me know if you have any questions. Yeah.
So yeah, actually I have a doubt. Actually, I have a doubt with the
Okay.
previous ROS one Move It also. Like if the goal position X Y Z, I think we can give it as a C
Yes.
program or CPP program or Python. But we get the join angles corresponding to that as an output of a service or something.
You are asking whether you are whether we can get the joint angles in in the program, right? Like after. Okay.
Suppose I do a real robot. I
Okay.
have the audience of that robot, and in system I'm giving the goal position x, y, z, and I
Yeah.
getting the join variables, so join angles, theta and theta to etc. And if I apply that, if I can directly apply the
Yeah.
theta and theta to the real robot, I can achieve
Yeah, I mean
like that. Can
that
I
is
do
what
that?
it is
Uh,
doing. Like when we do when we give the goal position, what is happening is that it is creating a trajectory. Trajectory is like a group of points over the time. Like for example, one second. Okay. So what you are seeing is like if you are giving a goal position, okay, and if you are doing the planning, you can see this movement, right? It is not like directly setting some joint angles. It is the joint angles over a time. That is called the trajectory. Okay, so basically if you do the planning in C or CPP or Python, it is creating a trajectory. Okay, and that trajectory is executing when we press this execute button. It is going to the simulation or hardware. Okay, so you will get this trajectory value when you do the plan. You will get the trajectory value. Okay,
Can I get the final join position then
it's
join
not
angles
the single joint
final
angles
the
basically. It is actually a trajectory with respect to the time. Trajectory is actually a collection of joint angles. So it is not like, yeah, that you will get.
yeah uh, yes. If suppose I just want to
Yeah,
experience this inverse kinematics, uh, if I give that XYZ, then the trajectory will automatically
yeah, yeah,
execute
yeah, yeah,
according to the move it as you show. Then final
yeah.
position, it will reach the goal. Then it will have many
Yes,
joint
yes.
angles, say theta 1, theta 2, etc. So can I see that, or I can get it as an output of
The
something, some service or
final
some
joint
message or some
angles, right?
topic or something?
Yeah, yeah. Final joint angles, you
Yes,
will get
yes.
it. You will get it because these all things are TF only. From the TF, you will get the you can find the angle, final angles. But it has to execute basically. Like what I am trying to say is, uh, like when we give the goal position, it is creating the trajectory, right? So when we execute this trajectory in the robot, you can compute the final joint angles using the TF or using the joint state. Like you can echo the joint state and you will get the current angles or current position, this one. So this is the, so when you give a goal position, I can show you that. You can see the joint state is actually changing. Okay, so using the joint state, you can able to get the final value. Okay, and also the
Got it,
trajectory
got it.
generation, you are getting an array of trajectory. So you can you can read through that array and find the final position as well. That also you can do. So maybe you can have a look onto the program. Uh, it's basically like set of APIs that giving by MoveIt, and yeah. So this is how. Let me check. Yeah. So this is how we are planning it. Like this is the goal position, and we are setting the target, and this is the plan, creating the plan happening for that. So the plan is having the trajectory. Okay, the plan, and you can actually go through that plan, and then you can find the final joint angles as well. Okay. Okay, Hari. Is that clear? Like, if you're doing with C++, is what I'm saying. Like, you can set a joint position, I mean goal position, and you will get the plan. This object is having everything.
Okay, okay, okay. That's right.
Okay, so you can just read
Okay.
it, and you will get the joint angles. Okay, okay. So we can conclude for today, and tomorrow we will be continuing with the programming side, and after that we will jump into the navigation. Okay, okay, everyone. Good night.